This is the IEEE Computer Society Distinguished Lecturer Webinar Series, brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to our Distinguished Lecture Webinar Series. My name is Kerry Cosby, and I'm the Chapters Manager at the IEEE Computer Society and oversee our more than 600 professional and student chapters around the world and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks before we get started. You can ask your questions in the Q&A, and Dr. Parhami will answer as many questions as he can following the presentation. Writing your questions, if you could, and if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded, and the recording will be made available after the webinar. Computer architecture continues to be a growing field. The Computer Society provides related communities, events, and other resources that enable continued learning and exploration. This year alone, over 1,000 articles have been published on computer architecture in the Computer Society Digital Library, and the IEEE Computer Architecture Letters publishes the latest research on technologies. Consider connecting with other computer architecture professionals via one of the 5 free technical communities related to this area, such as the Enterprise Architecture Special Technical Community. More information will be shared after the webinar. You can also learn more at computer.org. Architecture, we're bringing you today's webinar, 8 Key Ideas in Computer Architecture from 8 Decades of Innovation, presented by Dr. Behrouz Parhami. Since the establishment of computer architecture as a discipline in the 1940s, the field has seen multiple minor and major innovations in each decade. Dr. Parhami will present the most important innovation in each of the 8 decades and show how these ideas, when connected to each other and allowed to interact and cross-fertilize, produce the phenomenal growth of computer performance now approaching exa-op per second, billion operations per second level, as well as to ultra-low energy and single-chip systems. He will offer predictions for what to expect in the 2020s and beyond. I'd like to introduce our speaker. Behrouz Parhami is a professor of electrical and computer engineering and former associate dean for academic personnel, College of Engineering at the University of California, Santa Barbara. He received his PhD from the University of California, Los Angeles. His research interests lie in computer arithmetic, parallel processing, and dependable computing. In his previous position with Sharif, formerly Arya Meher, University of Tehran in Tehran, Iran, he was also involved in educational planning, curriculum development, standardization efforts, technology transfer, and various editorial responsibilities, including a 5-year term as editor of the Computer Report, a Persian language computing periodical. He's published over 300 papers in peer-reviewed journals and international conferences, a Persian language textbook, and an English-Persian glossary of computing terms. Professor Parhami is a Life Fellow of the IEEE, a Fellow of IET, a Chartered Fellow of the British Computer Society, a member of the Association for Computing Machinery, and American Society for Engineering Education. and a distinguished member of the Informatics Society of Iran, for which he served as founding member and president between 1979 and 84. Dr. Parhami, I'd like to pass the floor to you.
Okay, thank you very much, Kerry. It's a great pleasure for me to present this talk in the framework of IEEE Computer Society's Distinguished Visitors Program, particularly since this year the Computer Society is celebrating its 75th anniversary. I've been a member of the IEEE and of Computer Society for 49 years, nearly 50 years, so I've been part of this amazing community for 2/3 of its existence. And therefore, I've also witnessed a lot of these developments that I'm going to talk about firsthand. Most of them I've seen firsthand, and shared the excitement as each new development came about. Now, Kerry gave a comprehensive introduction to what I've done in my life. This is a graphical representation of my journey through academia and computer technology. I graduated in 1968 from University of Tehran, and a year later I went to the US for graduate studies at Oregon State University and UCLA. And then I went back to Iran in 1974, persevered there for 12 years, which included 7 years after the Islamic Revolution, and then decided that I wasn't being very useful in my role in Iran. I immigrated back to the West, went through Canada, and ended up at UCSB, UC Santa Barbara, in 1988, 33 years ago. In 2023, I'll be celebrating my 50 years in academia, which began at UCLA. So that's a big celebration coming up. Much of what I will say today comes from my 2 textbooks on computer architecture, a basic computer architecture textbook, and a book called Introduction to Parallel Processing. Both of these are undergoing revision, so the material comes from the books themselves or from material that I'm preparing for their revised forms. Now, I have too many slides for a 1-hour talk, so please don't be distraught if I skip some of them. I can always go back to those that I skip in case there are specific questions. But I'll just routinely skip some of the slides in order to stay within the 1-hour limit. Okay, now we are all fond of making top 10 lists or top N lists more generally. And we also like to criticize other people's rankings of various things. So for example, best colleges. When a list of best colleges comes out, we look to see if our university is included there and whether its ranking is high. Then if it is, we like that list. If our university does not appear there or is ranked low, we say, oh, this is a misguided selection. So the same applies to computer architecture, although my hope is that science plays a bigger role in the selections in computer architecture than in movies or video games or best books and so on. So please keep this in mind. Not everybody will agree with the 8 ideas that I select. So with that in mind, here are the 8 key ideas. From 1940s, the stored program concept, 1950s, microprogramming, 1960s, parallel processing, 1970s, cache memory, 1980s, pipelining, 1990s, FPGAs, 2000 GPUs, graphic processing units, and 2010 specialization or customization of circuits to perform specific jobs more efficiently. Now, this is there are 8 items on my list. Usually we like to have top 10 lists. Come back in 2040 for my top 10 list. 2 more ideas will be added to the list by then. Okay, now before going through those 8 items, let me present a very brief background about what came before. Now, the history of mechanical aids to computation goes back thousands of years. For example, the abacus is said to be about 5,000 years old. About 2,000–3,000 years ago, there were a lot of mechanical instruments, aids to astronomical computations, and many of them are available in museums. Mathematician Pascal built his calculator, mechanical calculator, in 1652. There were a lot of significant developments, but what's most relevant to our discussion today began with the work of Charles Babbage. He proposed 2 significant machines, the difference engine, which was basically a glorified calculator, and the analytical engine, which is generally acknowledged to be the first real computer. The analytical engine used punch cards, both for programs or instructions and for data, variable values that it processed. It wasn't a stored program computer, though, because the program had to be provided externally through these punch cards. Now, the difference engine, as the name implies, relied on the notion of difference in calculating functions. And in this table, I show you a simple example. Suppose the function f of x, x squared plus x plus 41 needs to be computed. So the third column of this table shows the values of f of x for x ranging from 0 to 5. If you find the difference between the consecutive values, 41 and 43, that's the second column of the table. The difference is 2, 43 and 47, the difference is 4, and so on. And then if you find the difference of the differences, so the difference between 2 and 4 in the second column is 2, 4 and 6 is 2. And if you continue this one more column, the third difference will be 0. 2 minus 2 is 0. So basically, in order to compute f of x for different values of x, all you need to do is to find f of 0, which is the first entry there, and that's basically very simple, it's 41, and then basically proceed in the following way. You know that in the first column, you always have 2. In the second column, let's say you have 2, and then that 2 added to 41 gives you 43. Then the 4 added to 43 gives you 47. So this is basically a quick way to compute that particular function for different values of x. And at the time of Charles Babbage, people were interested in constructing tables of functions. So let's say a table for logarithm, table for sine. Of course, logarithm and sine are not in the form of a polynomial, but they can be approximated by polynomials. And Babbage used 7th-degree polynomials to approximate various functions. Now, if you get a chance to see this machine, there are copies of this machine at several museums, including the Computer History Museum in the United States, San Francisco Bay Area. It's really a treat to see this machine at work. And they do have demos there once in a while that somebody puts the machine through its phases and shows how computations are performed. Now, the analytical engine was actually never built, although subsequently it was verified that the design was almost totally correct. With a few minor corrections, it could work. And people have built pieces of this machine, but the project to build an entire specimen of the machine has not yet been completed. Both Babbage himself and Ada Lovelace wrote programs for this machine. And because the machine was never built, the programs were not run, but again, they were verified to be correct later. So if you want to learn more about this analytical engine, this article referenced in this slide, IEEE Annals of the History of Computing, January through March 2021. By the way, these slides will be made available to you, so if you want to study them at your leisure, and including the slides that I skipped, they will be made available to you. Then came electromechanical and plug programmable computing machines in the early 20th century, and quite a few machines were built, and these are just samples. Turing's Colossus, which was a code-breaking machine, the ENIAC, Zeus's Z3 computer, and so on. So these were electromechanical calculators. Now we come to the first idea, the stored program concept. Various people have been credited with inventing this idea, although, beginning with computers, it's very difficult to trace a particular invention or innovation to one person, because a lot of collaboration existed and people sort of discuss ideas with each other. So there was this legal battle about who actually invented the computer, and there's a book about that. And that legal battle, they actually went to court. And through that legal battle, Atanasov was credited with inventing the computer in the form that we know today. Although ideas from Turing, Babbage, as I mentioned, Babbage programmed his analytical engine. John von Neumann, in fact, his name is more closely associated with computer than any of the other ones, and so on. So the idea of stored program was invented or thought of by Atanasov. Other people, including von Neumann, Eckert, and Muckley, actually visited Atanasov in his lab and brought with them some of his ideas that they used in implementing their versions of machines. The first stored program computer, again, there is controversy about which computer can be considered the first stored program. Around the late 1940s, a whole bunch of computers suddenly started being designed and started working. Sometimes one computer was designed before another one, but became operational later than that. So these are some of the machines from the late 1940s. Manchester Small-Scale Experimental Machine, EDSAC, Cambridge University, EDVAC, Princeton University, and BINAC, it was delivered in 1949, but really did not function. So we really should not include it in this list. Okay, there are two types of computer architectures. They're known as von Neumann architecture and Harvard architecture. Von Neumann architecture shown at the top, has a single memory unit where both data and code, data and program, are stored. The Harvard architecture had separate memories for data and program. And there's, of course, an advantage to separating data from program because we tend to think of a program as unchanging and data as being changing or variable. So putting the program in a separate memory sort of protects it from accidental changes that we do to data. On the other hand, using a single memory is more efficient because if you happen to have a small program with a lot of data, you can use the memory. On the other hand, for some problems, you had a large program with little data. So you're using memory more efficiently. More importantly, the notion of being able to change the code, especially in these days of machine learning, is a powerful one. So as I said, we tend to think of programs as unchanging. We sometimes put programs in read-only memory so that we can just read it and never change it. That protects the program against accidental damage. But then we do want to change the programs on some occasions, including, as I said, in machine learning, we can improve our programs. So both of these architectures are in use today. The idea I chose from the 1950s is known as microprogramming. So what is microprogramming? Well, in the early days of digital computers, people had to decide on what the computer is supposed to do, basically define an instruction set, the set of instructions that it should execute, and then build hardware, custom hardware, to execute those instructions. And once the design is frozen, you cannot change the instructions. You have to basically start over and build new hardware for a different instruction set. Now, this was both expensive and time-consuming. So several researchers, including Maurice Wilkes of the UK, who is credited often with the idea of microprogramming, said, okay, when a computer executes instructions, it essentially goes through phases or steps in executing the instruction. So in this diagram, you see, please ignore the legend. Those are not relevant to this discussion. This figure comes from my book on computer architecture, where this simple computer is introduced. So the legend corresponds to what this particular microprogram does for that particular instruction set. So the instruction must be fetched. That's the first step. The instruction must be decoded and its operands made ready, for example, brought out of registers. And then depending on the type of instruction, the microprogram branches. So for load and store instructions, it goes through this path. For jump and branch instructions. So a particular instruction is executed by executing these steps. Say this one, then this one, then this one, and we go back and execute the next instruction. So the computer is in a continuous loop, going around this loop through various paths. Sometimes it goes through this horizontal path all the way and then goes to the next instruction. So Wilkes called each of these, so all of these happen for executing a single machine instruction. So he called these micro instructions. So several micro instructions are executed to execute one machine instruction. And the structure of this looks very much like a program. So we have instructions in a program that are executed sequentially. Then we have branching. Okay. So this looks like a program. So he called this a microprogram. Now, the good thing about looking at it this way is that now each of these phases, so fetching an instruction from instruction memory, corresponds to asserting a certain control signals and deasserting some other control signals. Asserting means making it 1, and deasserting means making it 0. So if we store these assertions and deassertions in the word within a memory, which was called microprogram memory, then to execute this microprogram, we fetch this microinstruction, and that microinstructions will have zeros and ones for various control signals. Then we fetch the next instruction in sequence, and sometimes we branch. And therefore, we are executing program. Now, if we want to modify this hardware, for example, to correct an error we made in designing it, all we have to do is load different values in the microinstructions. And in fact, 2 completely different computers can be implemented using the same hardware. So this is the generalized hardware for a microprogrammed computer. I won't go through the description of the details. The key elements are the microprogram memory, where those microinstructions are stored. Microinstructions are fetched, and for one clock cycle, or one machine cycle, those control signals are allowed to operate. For example, transfer values between registers, read out things from memories, and so on. And then we go to the next microinstruction. And when we go to the next microinstruction, we either go sequentially. So everything is preceded with micro. We have program counter in regular computers. Microprogram counter is basically what allows us to go through different microinstructions. Sometimes we increment the microprogram counter, such as here when we go from one microinstruction to another one. Sometimes we jump, and we jump through these tables. So we go to different places depending on what class of instructions we are executing. So this piece of hardware, by just loading a different microprogram in this memory, can be turned into a different computer. It's a neat idea. From the 1960s, I've chosen the notion of parallel processing. And in fact, before we built parallel computers in the form that we know today, we had what was known as content addressable memory, and these are still in use in some applications. Binary content addressable memory cell and ternary content addressable memory cell. So this is a memory that not only stores data for us, but also does very simple processing in way of comparing things to each other. And therefore, because we compare all the word in the memory to some desired pattern, we are doing essentially parallel processing. But parallel processing in the form that we know today started with ELIAC-4, which was a computer designed and built at the University of Illinois in the 1960s, although it really did not become operational as a useful machine until 1975. But all the ideas and elements were there in the 1960s. And by the way, this is true for a lot of the other ideas. When I associate an idea with a particular decade, sometimes the seeds of that idea came earlier, and sometimes the idea actually matured and became practical a little bit later. But, I assign it to the decade where much of the work on that idea was completed. Okay, so this is ELIAC-4. It was what we call today a SIMD parallel computer, single instruction, multiple data. So there was a single control unit that issued instructions, and those instructions were followed by multiple processors synchronously all at once. And these processors had, in those days, memory was very expensive, so they had drum memory. So data was stored on tracks of a drum for the various processors. We also have what we call MIMD parallelism, multiple instruction, multiple data. This is where multiple processors execute more or less independent programs. And then in this version, there is a shared memory. Each processor has its own cache. I'll talk about cache in a few minutes. And then occasionally it goes to memory to fetch data. And then the processors collaborate in solving pieces of some large problem. We also have this version where there's no shared memory. Each processor has its own local memory. Processors can still access memories associated with the other processors, but requests for those remote, what we call remote accesses, must go through an interconnection network, so they take longer to process. If the processor wants a data that is in local memory, it can get to it quickly. If it wants data that is in a remote memory, depending on where it is, different amounts of time may be required in going through the interconnection network. So one challenge in running such multi-computers is distributing data to memories judiciously, so that most of the time the processor finds the data required in local memory and can access it quickly, and the delay of the interconnection network is paid only once in a while. Of course, we now have warehouse-sized data centers, which are essentially very large parallel computing systems. And in this case, you see that the servers or processors are put in large containers, and many of these containers sit there, and this is highly modular. You can remove a container if it fails and just bring in a new container to replace it, and there's networks. There are networks connecting these. One of the challenges in these data centers is cooling, so there's an elaborate cooling mechanism, and also these requires a lot of energy, so they're usually built near power generation facilities, and in fact they're built where power is inexpensive. So for example, in Oregon or Washington, where a lot of hydroelectric power exists and is relatively cheap, they set up these data centers to get cheap electricity. Okay, there is this site known as the Top500 Site that keeps track of the largest computers or supercomputers in the world. And this curve shows that the topmost computer in the world has been improving in performance steadily. So each of these triangles is one computer. Data points are provided until about 2016. But if you refer to subsequent data, this trend of increasing performance has continued. So nowadays, we are looking at roughly 1 exaflops, that's 10 to the 18 computations or arithmetic operations per second. That's mind-boggling, 10 to the 18. Petaflops has already been achieved, 10 to the 15, and so on. And of course, the supercomputer is shrinking. This supercomputer from 1997, it was known as ASCII Red, occupied 150 square meters of space, and it consumed 800 kilowatts of power, okay? Roughly 1 megawatt. Then in 2006, a Sony PlayStation roughly had the same computational capabilities as this machine, much smaller and only 0.2 kilowatts, 200 watts of power. And then we just have seen the release of iPhone 13, which has 6 CPUs and 5 GPUs in that tiny frame, and 16 neural network accelerators. It is even smaller than the PlayStation, uses less than half a watt. In terms of computational power, because it's optimized for different types of workload, it doesn't do mathematical computations. So it's hard to compare, but my guess is that it's roughly of the same power as this supercomputer. Smartphones are basically optimized for video processing. That's one of the major things they do. And and video processing does involve arithmetic computations, but it's not of the same kind. They're not directly comparable to what these supercomputers do. Okay, I'm going to skip this. From the 1970s, I have chosen cache memory, and Maurice Wilkes is often credited with thinking of this idea, although other people have thought of it too. So what is a cache memory? A cache memory is basically a memory that is very fast. And because it's very fast, it's also very expensive. So we have a small amount of cache memory. So these are basically different types of memories used in a modern computer. The registers sitting right next to this processor are the fastest. Then we have 1, 2, or even 3 levels of caches. These are increasingly larger memories. Okay, but as we go each level, they become slower. Then there's main memory. There's secondary memory, which is disk nowadays, although solid-state memory is also becoming commonplace. And then tertiary memory, these are basically archives where vast amounts of data are stored. So just to have an idea, this is the cost per gigabyte. The cost is fairly large at the top and becomes much lower as we go down. The capacity, on the other hand, goes in the reverse direction. And the access latency, so for registers, we have typically a nanosecond. A few nanoseconds for level 1 cache, maybe tens of nanoseconds. These are just rough numbers, round figures. Tens of nanoseconds for level 2 cache, hundreds of nanoseconds for main memory, and so on. So we have all these memories, and so the cache, what it does is tries to keep the most useful, the most frequently accessed data right here in the fast memory, so that whenever the processor wants to access data, very often, something like 95% of the time or 98% of the time, it finds the data here, so access it very quickly. Occasionally, it has to go to these slower memories and fetch the data into first level cache. So the average latency will be very close to the latency of this fast cache, given that 98% of the time the data is found there. Okay, so this is the idea of cache memory. So this is an analogy I use. If you're sitting at a desk and you're working on some tasks, the task that you're currently working on will be on your desktop, very easily accessible to you. So suppose you're doing your tax return. So the documents for this year's tax return will be here. Then there will be some other documents that may be sitting in a drawer here. Those are a bit less useful in terms of access, but they're still easily accessible. And maybe tax returns from prior years will be sitting in a file cabinet in the next room. So most of the time, because you're working on current year taxes, the things that you want are in your desktop. Now, if you suddenly see that you need to refer to last year's taxes, you get up and go get last year's taxes and put them here and then continue your work. So this is a simple analogy for cache memory. So in this case, the desktop corresponds to the register file, the fastest memory. The drawer corresponds to cache memory, and the file cabinet corresponds to main memory. Okay, so this is basically, let me skip that. So this is why cache memory works. This is from a paper by Peter Denning in Communications of ACM. It shows over time, as time unfolds, which parts of the address space is accessed by a particular running program. So this is address 0, address 1, address 2, and so on, all the way up to the entire address space of the program. And the black dots represent access. So in this particular time slot, all of these addresses were accessed, and this address over here was accessed, but all the white space correspond to addresses that we did not need in this particular time span, although these addresses will later become useful. Okay, so the idea is that at any given time, so if you take a slice, let's say over here, the program needs only a small part of its address space. And if you transfer that particular content, that particular data, into a cache memory, the program can run for a significant amount of time without needing anything else. So this is known as spatial locality, coming from space. So accesses are local in space. Also, once you use a particular data item, you tend to need that data item for a while. This is known as temporal, coming from time, locality. Okay, so once you bring some data that was not in the cache into the cache, then you tend to access it for a while. So all subsequent accesses to the same data will be very fast because you'll be accessing the cache. So the combination of temporal and spatial locality is what makes cache work. Makes you have that hit rate of 98%. And of course, the idea of cache is used in many other contexts. For example, we have something called disk cache. So a disk memory is a rather slow piece of hardware. Every time you want to go to fetch something from the disk, let's say a sector or a block of data, you have to move the head, read-write head, to align with the appropriate track. And this being mechanical motion is pretty slow. It's measured in milliseconds, whereas everything else in the computer is measured in nanoseconds. Then you have to wait for the disk to rotate so that the data is aligned with the head, goes under the head, and then you read the data, okay? So as you go, suppose you need this sector, you go and fetch it. One idea is rather than just fetch that one sector, fetch the content of the entire track, because as the disk rotates, the entire track passes under the read-write head, and you can read the entire track with just barely higher latency, okay? And put that track in a solid-state memory, a DRAM typically, and then the next time you need something else from this track, you don't need to go to the disk and pay all the latency of the slow disk. You can grab it from this solid-state memory, DRAM, okay? Again, spatial locality make this works because if you're reading a file, for example, you read a section of that file, it's very likely that other parts of that file will also be accessed in future. So using this idea of spatial locality, you sort of predict that you are going to need the rest of this track and therefore put the entire track in disk memory. We also have web caching that web service companies use. So for example, if you access a site like Amazon, you may have to go to the central servers of Amazon, but often content that is accessed by a lot of people is stored in local web caches so that you have a shorter path to those local caches to access that data. So it's a very general idea that can be used in different contexts. From the 1980s, I've chosen pipelining, and pipelining is an old idea, but the way it's used in computer architecture can be traced back to the 1980s. So here I've shown a computation of this particular expression. Involving an addition, a multiplication, a subtraction, another multiplication. So basically, you compute A plus B, multiply that by C times D, and so on. Pipelining basically says, okay, the latency of this computation is from the input to the output. And the critical path goes through this addition, this multiplication, this division, and this square rooting. So this much time is needed to find your result. However, if you provide storage registers at this cross-section, so the addition result is stored, the multiplication result is stored, the subtraction result is stored, then this part of the hardware is released and can be used for a second. So suppose you want to repeatedly compute this expression for different values of input. So once the results of this first stage are stored, you can use the first stage for another computation as the second stage takes over and so on. So you can be doing 4 different computations using the same hardware, augmented with these, what we call pipeline registers. So in computer architecture, this idea of pipelining was first used in vector processors, and Cray Computer Company was a pioneer of this type of processor, where function units such as adders, multipliers, and so on were divided into pipeline stages so that one multiplication may take a long time, but you can do many multiplications at the same time using the idea of pipelining. So the first multiplication, when it moves to the second stage of the pipeline, you can start another multiplication. And combined with vector registers that could store an entire vector, this can be used to do vector processing at a much higher rate, because now the effective rate of multiplication is the latency is dictated by the latency of this one stage rather than the entire latency of the multiplier. Okay, so this is the idea of pipelining used in instruction execution. Okay, so an instruction is executed by fetching an instruction from the instruction cache. Notice that this is the Harvard architecture. The instruction cache and data cache are separate. Then the register file is accessed. Then the arithmetic logic unit does some operation on the operands fetched from the register file. Then perhaps the result is stored in the data cache, although for some instructions no storage takes place. And finally, the result may go into a register file. Okay, so once the instruction is fetched and is stored in this register so that the register file can be accessed, the next instruction can be fetched. and therefore we can have up to 5 instructions at various stages of execution using the same hardware. Without using 5 processors, I can execute 5 instructions at once. Now, the caveat here is that when one instruction is fetched, how do we know which instruction to fetch next? Well, if the program is running sequentially at that point, well, we just increment the program counter and fetch the next instruction in sequence. Although if this instruction that I just fetched happens to be a jump or branch instruction, then at this point, we haven't yet executed the instruction, so we don't know whether the branch will be taken or not taken. So our hope is that branch instructions and jump instructions are infrequent, so that most of the time we are running smoothly, filling the pipeline. And if the instruction happens to be a jump or branch, we try to resolve the condition for the branch as quickly as we can. And we use a method called branch prediction to predict which of the 2 paths the branch will specify, and then fetch the next instruction from that more likely path. And then in case we are wrong, then we can go ahead and nullify those instructions. Okay, so there are other issues. For example, here is one issue. So these are basically instructions written in symbolic form. This means that the contents of register 8 is added to the contents of register 6, the result stored in register 8. Then in the next instruction, the contents of register 8 is added to register 2 and stored in register 9. This is just, a simple program. Therefore, this next instruction here, the third instruction here, uses the result from the second instruction. The second instruction is running here in this pipeline. It will store its value into the register file in this stage, in cycle 6. Whereas this instruction needs that result in cycle 5, because that result should be given to the arithmetic logic unit to do this addition. So the result will be available in a register over here, but it's needed by the next instruction over here. Okay, so a trivial way of dealing with this problem is just to stall this instruction. Say, okay, wait until this result is stored, and then do the ALU operation in this cycle. But that will waste time. A method called forwarding or data forwarding is used. There is a sophisticated control mechanism here that detects this dependency condition. This is known as data dependency. And then sees that this ALU needs a value that will be stored in the register here, but that value was actually computed here. So it's already available, it's just not in the register. So that value can be forwarded directly through hardware to the ALU. Eventually, it will also be stored in the register, but meanwhile, this next instruction can proceed and complete its task. So through these ingenious mechanisms, data forwarding, branch prediction, we try to keep this pipeline as full as possible so that many different instructions are executed at once. Now, this 5-stage pipeline is very simple. Modern processors have much deeper pipeline. By deep, we mean there are more stages. So there may be 20 or 25 stages in the pipeline. Therefore, a lot of concurrency exists. Okay. From the 1990s, I've chosen FPGAs. Again, FPGAs in rudimentary form, programmable logic arrays and programmable array logic, I won't go into the distinction, existed much before that. But in the 1990s, we started putting a lot of complexity into these field programmable gate arrays that consisted of logic blocks, a bunch of interconnects or just wires, and switch boxes. And we could actually map a particular hardware onto this FPGA by doing part of the logic in this logic block. Each of these logic blocks is fairly simple. And then the output of this logic block may have to go to another logic block for the continuation of work. And that is done by routing the values. So each of these heavy dots here is a programmable connection. So we can have this horizontal line connect to this vertical line. Through the switch box, that line can be connected maybe to this horizontal line, and through this programmable connection to this logic block. So by programming these connections and programming the logic blocks in terms of functionality, we can implement pretty much anything, any hardware function. Now, nowadays, FPGAs have many thousands of logic blocks, many thousands of wires. And there's so much capability in here that the processor, such as an Intel processor, can be mapped into this hardware using a small fraction of the resources. So maybe 100 logic blocks out of many thousands. And so we can map mind-boggling complexity onto these FPGAs. And FPGAs nowadays are everywhere. They're used everywhere. In aerospace and defense, medical electronics, automotive control, software-defined radio, encoding and decoding. Altera and Xilinx, shown in this diagram, are two of the key players in FPGA. Okay. From the 2000s, I've chosen GPUs, graphic processing units. GPU, the name comes from the fact that these units were first developed to do computer graphics in order to display things on your display unit from your computer, and in particular for gaming systems, where graphics is really an important element in the game environment looking realistic. However, later they became more general, and we still use the name graphic processing units, but they're used for much more than just graphics processing. So here is a simple diagram to show you the difference between CPU, central processing unit, this is basically the processors that we are used to, and GPU. In a CPU, let's say in a multi-core chip, there may be several ALUs, a control unit, a cache memory, and DRAM. In GPU, basically cache memory has been removed, and instead more cores, simple cores, have been added. So there's a lot more computational capability. So these two charts show capabilities of GPUs compared with CPUs. So the green line is NVIDIA GPU doing single precision floating point arithmetic, gigaflops per second. The light green. The dark green is NVIDIA GPU doing double precision arithmetic. Of course, that's a much more complex operation, so the rate goes down. Now compare this to what CPU, Intel chips do for single precision and double precision. So the computation rate is much higher. And data rate is also much higher. The amount of data that can be processed per unit time is much higher for GPUs. And this is why GPUs have become a fixture in most of today's very high performance computers, supercomputers. So almost all of the very top computers on the top 500 list today use GPUs alongside CPUs. They use both of them to boost the performance of the system for numerical computations, which are basically what these supercomputers are used for. Scientific modeling, huge models with a lot of data and a lot of computation. Okay, so of the things that I discussed so far, the ones that I've shown in black here are methodological, can be viewed as methodological advances. This notion of stirred program, microprogramming, FPGAs. And the ones shown in red, parallel processing, cache memory, pipelining, and GPUs, can be viewed as performance improvement, doing the same thing but faster. Okay, not doing different things. That brings us to 2010s. But before that, let me show you this chart that shows from 1985 to 2010, about 2.5 decades. The trend in performance improvement, and the blue dots show performance improvement as a result of just technology advancement, gauge speed improvement. So technology became faster, so even if we just implemented the same architectures as in 1985, in 2010, we would have a factor of about 100 higher speed by virtue of gates and technology being faster. Another factor of 100, roughly 100, was due to architectural improvements. Okay, so, and these are the ones I discussed, using cache memory, using pipelining, and so on. So technology advancements and architectural improvements contributed roughly the same factor in performance improvement over the period 1985 to 2010. Now we get to 2010s. Where we went back to specialization. We sort of shied away from specialization in the interim because specialization costs money. If you build a hardware to do just one thing, that's very expensive because you have to spend a lot of development time and cost to develop that one thing. Whereas if you develop an FPGA, well, you invest a lot of money in developing it, but then it can be used for different functionalities by programming it. Okay, but because we needed to improve performance and we sort of came to a dead end in both technological speed improvement and architectural improvements, we went back to specialization. Okay, so this, as you see here, CPU is very general purpose. Okay, so it's highly flexible because you can program different things on it. GPU is a little bit less flexible. It's mostly doing numerical things. ASIC is least flexible. You build it, and this is application-specific integrated circuits, because you build it to do just one thing or a small class of things. On the other hand, the performance of this specially developed ASIC will be much higher than CPU. So if you want to gain performance, we have no option but to go back to these ASICs. So here I show that ASIC has an initially large development cost, but if you increase the volume, each additional unit does not cost much. So if you have a product like iPhone that will be sold in many millions, then developing ASICs for it makes sense because you put in that investment, and then each additional iPhone, you don't spend much. You just build the same circuit over and over again. Whereas with FPGAs, the development cost is low, but then as you build more and more units using FPGAs, the cost goes up. So at this crossover point, it makes sense to go with ASIC. It starts making sense to go with ASIC. Now in 2017, Hennessy and Patterson, two of the pioneers of developments in computer architecture, gave a Turing lecture, ACM Turing lecture, in which they predicted the new golden age of computer architecture, in which domain-specific hardware will dominate. Okay, they observed that further progress in conventional architectures was impeded by slowing Moore scaling. Moore scaling is what, Gordon Moore had predicted, that integrated circuits will continue to shrink and improve in performance at a fixed rate. But that rate lately had started to go down, and we got into a saturation state. Now, Dennard scaling basically says that power efficiency improved, and again we got into what we call a power wall, meaning that once you put 200, 300 watts into a microprocessor, there isn't room for more power because disposing of that, the heat generated by that power, is extremely difficult. So they predicted that we will have domain-specific hardware and domain-specific languages to go along with them. And then they also predicted that we will have something called free open architectures. Just as we had open source software, we will have open source architectures where everybody can collaborate in improving and enhancing them. Okay, an example of a domain-specific piece of hardware is Google's Tensor Processing Unit. It's basically an accelerator for matrix operations. And in this table, you see various versions of TPU, version 1 through version 4, and also another version, Edge. And the power used by this tensor processing unit ranges from 75 watts for the early model to 450 watts here, and then they made it more power efficient there. And then the processing capability, processing power, started from 23, doubled in the next version, again doubled in the next version. And even though the numbers for here are not available publicly, the guess is that another factor of 2. So a factor of about 10 improvement over these generations within a few years, only 5 years. Okay, I'm going to skip this in the interest of finishing on time. So now I'm going to do in a few minutes some technology forecasting. And forecasting for anything, whether it's weather or stocks, is a dangerous thing, because very often your forecast doesn't come true and you get flack for not predicting things correctly. And in fact, there are these anonymous quotes about forecasting, one of which is, forecasting is the art of saying what will happen and then explaining why it didn't. And there are 2 kinds of forecasts, lucky and wrong, and so on. There are quite a few of these. So with that warning, here is my predictions for 2020s and beyond. We will have design improvements and performance improvements as before. So here are some things to look forward to. Adaptation and self-optimization or learning. Machine learning is everywhere. There's no reason not to have it in computer hardware. Computer hardware of the future will adapt itself to changing conditions and will self-optimize. Security is a big problem. One of the areas in computing that we have failed miserably is to provide adequate security. Every day you read stories about, these supposedly giant tech companies with claims of having very secure systems being hacked and user data compromised. And the belief nowadays is that we have to do some sort of hardware implemented security because software implemented security is not working. So a lot of research teams worldwide are working on this issue of making hardware secure to begin with so that everything you put on it, the software also is secure by virtue of the hardware being secure. Reliability through redundancy and self-repair. That's one of my areas of specialties, fault-tolerant computing or dependable computing. Logic and memory designs. Basically, we have now encountered what is known as memory wall. Our processors are working very fast, but the memory cannot keep up with demand for data from the processors. Okay, so the thinking is let's move some of the processing inside memory so that we don't have to bring data out of the memory in order to operate on it, but we can operate on it in place while residing in memory, so that the load of the channel between memory and processor is reduced. Occasionally, you still have to bring stuff to the processor, but most of the times, we hope to be able to manipulate data while it's inside memory. And finally, one of the things that is coming back is analog computing. Now, analog computing is not very precise. However, in many applications, including machine learning, we don't need a lot of precision. So the speed of analog computing is once again an asset. And we are thinking in terms of combining analog and digital circuits in order to basically benefit from the advantages of both, accuracy of digital and speed of analog. Okay, what about performance improvement? Well, we are looking at revolutionary new technologies. All of us have heard about things like quantum computing, for example, which promises to provide orders of magnitude speed in solving some problems. Although, practically it has not been very successful yet, but there are technologies like that around. And new computational paradigms, different ways of solving problems other than the standard algorithms that we are used to these days. And in particular, the biologically inspired computing or brain-inspired computing. Speculation and value prediction. Well, in the early days of computing, hardware was expensive. So we tried to use it efficiently, not do more than the minimum required because it would take a long time. But nowadays, hardware is cheap. And especially if we go to biologically inspired computing, hardware will be cheap and also very low power. So we can afford to do what is known as speculative computation, do computation whose results may or may not be needed. If they are needed, then we are ahead. We have already computed them. And if they're not needed, then we just discard those results, having lost very little in terms of energy and time. And finally, the last domain is better performance per watt. The power wall is already here. As I mentioned, microprocessors use hundreds of watts, which is basically the limit of what we can dispose of these days. Supercomputers are using many megawatts. They're approaching gigawatts of power. And therefore, a supercomputer center operator faces a huge electricity bill every year. One of the major costs of running a data center is paying the bill for electricity. So whatever savings we can achieve there will go a long way towards reducing the operational costs. Okay, this is the end of my presentation. Again, I'm going to skip some of these. Oh, sorry. Let me say just a few words about this slide. We need more than sheer performance. Of course, we want to have very high performance. We want to have very low power consumptions. But in parallel with that, we have to shift towards environmentally responsible design. Things like reusable design. Nowadays, electronics get obsolete every few years. And there's a challenge getting rid of all the obsolete iPhones, all the obsolete computers. So if we can design systems to be reusable and also use less energy, that's a good thing to do. Starting in 2016, IEEE started publishing IEEE transactions on sustainable computing. So IEEE became aware of this, the need to work in this area. And I was lucky enough to be on the editorial board of this new transaction since then. I'm still on the board. And we hope to make a difference in this area of sustainability for computing. Okay, let me stop at this point and see if there are any questions.
Thank you for your presentation. That was great. We've got quite a few questions here. We'll try to get to a few of them. One of the questions that we have is there an official standard to say what solid-state drive is? I was faced with an issue where I bought a fake SSD and was wondering if these items are standardized, that one can say this is an SSD, HDD, etc. I was able to get reimbursed after a month of stress and arguing, and the fact that it functioned nothing like as specified, but I was wondering, is there a standard?
Yeah, not to my knowledge. That's true. Claims that tech companies make, it's very hard to verify because these things are packaged and you can't look inside. There's no way. So, for example, if they use a disk with a large disk cache, it may look functionally very similar to an SSD because most of the times you get your data rather quickly through the disk cache. There isn't. In fact, let me give you an analogy. I'm just reading a book called Bad Blood. It's about the Silicon Valley startup Theranos claimed to do blood tests based on finger prick rather than drawing blood in the conventional way. And what they did, most of the time, they got the sample and they actually ran the sample through conventional devices. So their claim was that they're doing this new technology, but they were really doing old technology underneath. And they got exposed, of course, and the trial is going on right now. So no, there is no way to verify that. I'm glad that you got reimbursed for it. But as long as the device behaves like an SSD, there's no way to verify whether it is actually an SSD. The performance is actually the main thing, right? How quickly you can read and write data.
There is a question here. I'm not sure which slide it's referring to. but it says Windows automatically chooses which to use. Does Windows do a good job of this? Can we control GPUs with emulators like WMware or VirtualBox or Hyper-V?
Okay, I didn't get the first part. Windows chooses what automatically?
It looks like it's during the section you were talking about the GPUs.
Okay.
That seems to be when it came up. So it says Windows automatically chooses which to use. I'm sure that fits into your GPU discussion.
Okay.
It says, what does Windows do a good job of this?
Yeah. So GPU, a computer that has both CPU and GPU, the software developer can use either resource depending on what is being done. Apparently, the questioner suggests that this is done at runtime. I'm not familiar with that. The way I see this is that your system may have a GPU. If you're running old software on your computer that was unaware of the existence of GPUs and benefits of GPUs, it will be running on the CPU, so that GPU does not provide any additional benefit to you with old software. But software that was developed recently with the awareness that there was this GPU can offload some of the computations to the GPU and take advantage of the processing power of the GPU, thereby running your programs faster.
Okay, very good. The next one says, this is not really a question, but an expression of excitement for the professor's prediction of hardwired security systems. I just thought I'd share that one with you. You don't have to answer anything on it.
Okay. Yeah, a lot of people are excited about that because, as I said, software security has failed miserably because, the secureness of the solution is based on a number of assumptions that don't hold in practice. And, all the hacks that we see are proof that those assumptions are misguided. So if the security is embedded in hardware, it still wouldn't be impossible to hack it, but it will be much harder to hack.
This next one, the person says, in 2010, I heard about dark silicon, the TDP wall. What happened? So I'm guessing that kind of disappeared. So what are your thoughts on that?
Okay. Dark silicon is basically the silicon that we put on chips and is not used or is not used most of the time. And we can afford to do that because transistors are cheap. We can put billions of transistors on a chip and use only several millions at any given time. Okay? So that dark silicon sits there. Ideally, it wouldn't use any power, although it may use some power, some leakage power may exist. So the idea is that we put a lot of resources and then use only part of the resources that are needed for a particular computation. The part that is not used is referred to as dark silicon. It's not an issue now because, silicon is cheap. Transistors are cheap.
Okay, very good. The next question is, what is your opinion about quantum computing?
Okay. I'm among the skeptics. Some advancement has been shown, but even the most avid supporters of quantum computing concede nowadays that it's not going to be a general purpose computer. It will be sort of an accelerator or a resource that can be made available for some computations, provided we can actually build it in a way that we can put it in a PC. That's not for sure yet. We are doing it in laboratories with a lot of equipment and cooling methods and so on. So if we can put it in the computer, it will be sort of like a special purpose device so that on algorithms where quantum computing is known to provide speed up, we can use that in exactly the same way that we are using GPUs nowadays. So it won't be, you won't, in my view, you will never have a quantum computer in which everything in your computer is based on quantum computing.
Okay, very good. A lot of our audience are asking about whether this is going to be recorded. It is currently being recorded. Each of you will be getting an email after this, and it will have a link to that recording. It'll also be on YouTube and on our website. Let's take one last question. I know we've gone quite a bit over here. So this next one is, would you be so kind as to say several words concerning the new fault-tolerant paradigms?
Okay, well, fault-tolerant paradigms are not really new. I've been teaching a fault tolerance course for nearly 45 years, except that they are now moving from the domain of exotic systems into ordinary systems. And this is the standard way in which technology develops. So, for example, NASA has been using fault tolerance for its spacecraft computers because once you send a spacecraft up, there is no possibility of maintenance. So you have to make it highly reliable and also self-repairing in a way, so that you put multiple computers on board the spacecraft. So, for example, the space shuttle had 6 computers on board. 5 computers. And then 3 of them were operating at the same time, so that the results could be compared. In case one of them was wrong, you could still get the correct result. And then the other 2 were spares, so that they could be switched in case one machine permanently failed. Later in the life of Space Shuttle, there were actually 4 operating computers and 1 spare, but that's a minor detail. So now we are putting these techniques. So, for example, error correcting and error detecting codes are used routinely in computer systems. That's one area of fault tolerance. So if you have an error correcting code, if 1 bit flips by accident, you can correct and get the correct data. And various other ways of reconfiguration and so on are used routinely. When you build a large chip with a lot of components on it, it's very likely that many of those components will be defective right at the outset. And therefore, you need to circumvent those defective components and not use them in favor of the components that are good. So all of these methods that have been used for a long time are finding their way into conventional, the computers that we have on our desktops. Therefore, as a result, new methods are also being discovered, given that it's now even more important than before.
Okay, that's great.
One thing, let me mention just one other thing. You mentioned about the recording, but not about the slides. The slides will be made available.
Yes, the slides will be made available. They're actually, people can get them in the related content right now, but they'll also be in the email.
Okay, good.
So let me just take this moment to thank you, Dr. Padhami, and I'd like to thank our audience for attending. The upcoming webinars for October are Virtual Presentation Skills for Engineers by Roger Granis. That'll be in our Build Your Career webinar series. And in the Distinguished Lecturer webinar series, we have Secure Sourcing of COTS Products, a Critical Missing Element in Software Engineering Education by Nancy Mead and Daniel Shoemaker. The Future of Workforce by Dejan Milojevic. Why Technology Projects Fail by Steve Andrioli. This event's going to be brought to you by the Distinguished Visitors Program and in partnership with the IT and Practice Special Technical Community. And in our Standards webinar series, we'll have IEEE Learning Technical Standards Committee in action. Registration is now open. open for these, and we will be sending you a link to these future events along with the recording and the slides to this webinar. Again, Dr. Padhami, thank you very much for your presentation. It was great.
Thank you for the opportunity.